Hello everyone, my name is Andreas Glatz and I'm a technical customer support specialist at Flexoptix, and with my team in our daily work at troubleshooting, we sometimes receive tickets where IP engineers run into issues with some basics of optical communications. So this is the main reason why I'm presenting here about optical foundations, and I will give a brief introduction to several optical basics. So I will start this presentation by giving a short explanation why it actually matters to know something about optical communications as an IP network engineer, and why it can help to have a mental model about it. Further on in the presentation, I will give an introduction to the optical foundations, and in the end of the presentation, I will wrap it all up. So let's dive in with a question. Why optical communications matters for IP engineers? So optical networks have a really high performance, allowing high capacities, transmission over very long distances. So they're building the physical backbone, connecting data centers, connecting cities, providing long-haul links and so on. And most internet traffic is fundamentally riding over optical fiber. On the edges of optical spans are often IP devices, and eventually every packet is getting transmitted over an optical fiber. So here's where the boundaries of the performance are set, and here's also a source where network issues can appear that you may see as an IP engineer in a layer 2 or layer 3, for example, as a packet loss, and having a certain mental model about it can help with avoiding guesswork if an issue occurs, and with faster troubleshooting, and also help with collaboration with optical teams, field teams, and so on. And through the IP optical convergence that is increasing, it is nowadays even more relevant than before. So let's dive in with some foundations of optical communications. Let's start with the transmission medium, the optical fiber, which consists of 3 parts. So on the left side, you can see a cross-section of an optical fiber, which consists, as you can see here in blue, of the core, the fiber core, which guides the light, the cladding, which is there to confining the light inside the core, and the coating, which is basically providing protection from physical damage, moisture, and so on. If you take a look at the right side of the slide, you can see that the light is the lasers aligning with the core of the optical fiber, and the core and the cladding are both typically made of silica glass with a precisely controlled refractive index. And as the refractive index of the cladding is lower than the refractive index of the core, there's a total internal reflection inside the core, so the light is bouncing inside the core basically and is getting trapped there until it reaches the end of the fiber, the receiver end. Usually there are many links which use separate fibers, one optical fiber to send a signal and another optical fiber to send a signal back, so to receive it. But there are also bidirectional applications where you use only one optical fiber and you send from both sides, receive at both sides, by using different colors of the light. So you're using different wavelengths, which leads to that these different colors of light are not interfering inside the optical fiber. The most common optical fibers are the multimode fiber and the single mode fiber, which you will see basically in every optical network. One of the main differences is the core size. In the multimode fiber, the core the core is larger. It is 50 or 62.5 micrometers in diameter. And as the core is larger, sending light into the core leads to that the light can take different paths through the optical fiber. And as the light is taking different paths, at the receiver end, the light has different arrival times, which leads to a broadening of the light pulses at the receiver end. And if the distance is increasing as larger as the distance gets, as more broadening and signal spreading you have, and at a certain distance, the signal cannot be detected anymore properly. That's why multimode fibers have only use cases for short distances, as they have the modal dispersion, so the light is taking different modes, different paths inside the fiber core. Advantages: you need lower cost optics, you don't need as precise lasers as you have a larger core, they don't need to be aligned as precisely with the multimode fiber core, but you have only shorter distances. Usually hundreds of meters, in some special cases up to 2 kilometers. And then on the other side, hello? Can you help? Hello? Can you help with the sound? Oh, okay, the sound is there again. Okay, on the other side, the single mode fiber, which has a small core, and as the single mode fiber has just a small core, it only allows the light to travel one path through the fiber core. So you only have one path. So this transmission is not limited by a modal dispersion. The single mode fiber, though, is limited by chromatic dispersion. As light has different colors, different wavelengths, those are traveling at different speeds through the optical fiber, which also leads to a signal spreading, but this is more relevant at way larger distances. So single mode fiber can be used for way longer distances, hundreds of kilometers or even thousands of kilometers, using amplification at intermediate sites. But for single mode fiber applications, you need high cost optics, more precise lasers that need to be more precisely aligned with the core of the single mode fiber. So those are the two most common fibers in optical networks. Maybe just a short introduction of the multi-core fiber, which is not so much used currently, but is an interesting technology that is more compact by providing multiple cores inside one optical fiber. So that will be interesting how that will proceed. Here you can see some of the most common fiber connectors. I listed the three most common ones. There's the LC connector, the lucent connector, which comes in a small form factor, can be used for very high density applications and high density environments, has a practical push-pull latch mechanism, and it has only one fiber inside, but one LC connector can be coupled with another LC connector, so you have a duplex connector. Same is working with the SC connector, also has one single fiber strand, but can be coupled with another SC connector to have a duplex connector. The SC connector, though, is not used anymore that much. It is more in legacy applications, and it got replaced by the LC connector, which is just half the size of the SC connector. Then there's the MPO connector, the multi-fiber push-on connector, which has inside the connector many fibers. So it has 8, 12, 16, or even more fibers inside the connector, which enables a parallel transmission of optical wavelengths over multiple fibers. So these are also called parallel optics. And there's a trademarked version of the MPO, the MTP, which comes with a better precision. One very important point here that leads to network issues is always clean your connectors. Even a little bit of dirt can, if connecting the connectors together, can lead to a damage. So always keep that in mind. Each connector has a certain Polish type, a ferrule that is aligning the optical fiber. A ferrule is made of is like a ceramic tube that is aligning the optical fiber at the end face of the connector to create the physical contact. And there are different Polish types, different physical contacts. There's the PC, the physical contact, which leads to a back reflection at around minus 30 dB, but more commonly used is the UPC, which also has a straight polish, and if aligning the connectors, it has a back reflection below minus 55 dB. And as you can see, the end face is straight, so it has a certain back reflection, and that is identified by blue connectors. So if you're seeing blue connectors, you already have the identification of it. And then you have the APC, the angled physical contact, which has a lower back reflection at below minus 65 dB, and it is angled. So the end face is angled. Why is it angled? It lowers the back reflections if creating the physical contact, and especially if using high power applications, optical systems with high power. If creating the contact, the back reflection is not going down the core of the optical fiber, it's getting reflected inside the cladding, so it's not through the back reflection damaging optical equipment like amplifiers, which can be very expensive. So always keep in mind that the connectors have identifications in blue and in green to identify the physical contact you're using, and never mate together UPC and APC that will lead to creating physical damage or heavy signal losses. So we talked about the transmission medium, the optical fiber. We talked about connector types. Then you need transmitters that are taking the electrical signal, converting it to a light signal, to light pulses. And on the receiver side, you need receivers that are taking the light, detecting it, and converting it back to electrical signals. So these are very, here are some common examples. There's the LED transmitter, for example, which is not a very precise source of sending the light, which is why it was used only in legacy applications and got replaced by the VCSEL, the vertical cavity surface emitting laser, which is already more precise, but also a laser that is used for applications in multimode fibers, standard in data centers as short reach optics. And then there are more precise lasers like the DFB laser diode, the distributed feedback laser, which can be used already for long reach applications, can be used in single mode applications for long haul links over long distances. And there are more transmitters. Here I can refer to a presentation from Flexoptix called Channel Mania, which is going into more detail about transmission technology. On the other side, the transceivers. Here are some examples. The PIN photodiode, which is a simple, stable, low-cost receiver used in many Ethernet optics, which has a standard sensitivity. So the optical receiver sensitivity is important to detect the signal, and as better as the sensitivity is, as longer the arriving signal can be in power and still can be detected. The APD, the avalanche photodiode, is a more complex receiver technology with a higher sensitivity. Here's a trouble some customers went into by overloading the receiver, by sending with a too high transmission power, not using any attenuators on the optical link, and damaging the avalanche photodiode. So this is always important to keep in mind with setting up an optical link. And then there are more complex receiver technologies like coherent receivers, which are using multiple photodiodes, which are using digital signal processing for advanced error correction and so on, that can detect optical signals that are heavily modulated in the amplitude of the signal and the phase and the polarization of the signal and so on. And also here I can refer to another presentation of Flexoptix that is about coherent transceivers. So transmitters and receivers usually come in a packet. As you can see here on the slide, there's a transceiver, so it's a device that can send and receive a signal at the same time. And this is an example of a SFP28 transceiver. It's a small form factor, pluggable to transmit, for example, 25 gigabit Ethernet. So there are different transmission windows which are referring to at which wavelengths and which ranges you can send wavelengths or colors over an optical fiber, and they are defined by how much, in which range they are. And here it is very important to take a look at the loss profile of an optical fiber. Here we have an example of the G.652 fiber, which has a loss, as you can see in the graph, which is different at different wavelengths. And there are some very common wavelength windows that are used to send over an optical fiber, usually because the attenuation there is lower. So we have the window at around 850 nanometers. So here you can see on the diagram that the loss at 850 nanometers is quite high, but it's used for short reach applications, and the lasers are pretty cheap, so this wavelength is still used to send over optical fiber. Then there's the O band, which you can see in yellow, at around 1310 nanometers, which can be used for medium distance links. In that range, you have already a lower attenuation in the optical fiber. And then you have the C band in green at around 1550 nanometers, which has the lowest fiber attenuation. So here, this is the primary band for long distance transmission because of that. That is a very important reason. And in blue, the L band has similar characteristics to the C band. It has a slightly higher attenuation. Often it serves as a capacity extension of the C band. So if you use an optical fiber and you want to use more capacity, you can also utilize the L band. Just one important thing to mention here is that this is just one type of optical fiber. There are other optical fibers with a different loss profile. For example, this fiber has a water peak at around 1400 nanometers, but there are other single mode fibers that have a low attenuation here as well. How is it possible to enable really high capacities in optical transmission? Very important technology here is the wavelength division multiplexing, which is basically using a passive device, a filter, a multiplexer, which is combining many optical wavelengths, or you could also say many colors, combining them into one optical fiber. So you can send many channels, many wavelengths that are combined through a multiplexer over one optical fiber. The two most common wavelength division multiplexing technologies are the CWDM and the DWDM. The CWDM multiplexing, the coarse wavelength division multiplexing, allows up to 18 wavelengths by using the optical spectrum. And if you take a look at the graphic on the bottom of the slide, you can see that the CWDM technology is taking a broad amount of the optical spectrum. That's because the lasers are less precise and they have a more wide channel spacing, and because of that, they can only be transmitted to up to 80 kilometers, or depending on data rate, also over longer distances. The advantage is, as you're using less precise lasers, less precise technology, the CWDM is more cost-effective. On the other side, you have the DWDM, the dense wavelength division multiplexing, which is only utilizing the C-band and the L-band of the optical spectrum. So these are the bands in the optical spectrum with the lowest attenuation. And therefore, you can send over longer distances, and you have more precise lasers. So the channel spacing is thinner, it's more narrow, and you can use more channels than in the coarse wavelength division multiplexing. But the DWDM solution is more expensive, but has also higher performance. More channel can be utilized, and you can transmit over even thousands of kilometers if using amplification. There are several optical signal impairments that reduce the power and the quality of an optical signal. We already talked about the attenuation by looking at how high the fiber loss is in an optical fiber, depending on which wavelengths you are sending. So you have a power loss over distance sending a signal through an optical fiber. Depending on which wavelength you are using, depending on if you're using a single mode or a multi-mode fiber, and also depending on how many connectors you are using. Because of using connectors, you have a certain insertion loss and also macro bands of the optical fiber, and splices can lead to additional attenuation, so to additional power loss. Then there's the dispersion, which is referring to how the signal is spreading over time. So at a certain time, the signal, the impulses at the receiver side are too broad, are overlapping, cannot be detected properly anymore by the receiver. And there are two examples which I already talked about. The modal dispersion, which is occurring in the multimode fiber, as light is taking different paths. So the light has different arrival times at the receiver end, which is leading to signal spreading, which is mainly limiting multimode fiber applications. And then the chromatic dispersion, which is that light is consisting of different wavelengths of different colors that are traveling at different speeds. So you also have different arrival times at the receiver end, but more at over large distances. This is a important value. An example here is a CWDM use case with, for example, 10 gigabit sending a signal over an optical fiber at a wavelength of 1310 nanometer, which works great with the attenuation values. Over 1610 nanometers, for example, the dispersion is too high and the link won't work at a certain distance. So dispersion can also be a limiting factor Then there's the noise, which is referring to the quality degradation of a signal. You have non-linear effects that are appearing by, for example, using amplification. Amplification is adding noise to an optical signal, and is more a limiting factor if using complex optical systems that are transmitting over very long distances. So you're using an amplifier to boost the power of a signal. So if the attenuation is a problem, you can use amplifiers at intermediate sites, but they're adding noise until the signal has a too worse optical signal to noise ratio and wouldn't work anymore. There are other reasons for non-linear effects for noise, for example, if using too high optical power levels. So this is the second last slide about the optical link budget, and you can think about it like that. On the right side, you can see an optical link with different events of fiber loss through the attenuation in an optical fiber, through signal power loss, through using several connectors, using splices and so on. And to figure out if a link will work, you need to know the link budget of a transceiver, and for that you need the minimum transmission power, the minimum receiver sensitivity, and the difference of that is the link budget. And the link budget needs to be basically higher than the link loss. So the total loss that appears through these different events of an optical link that are leading to signal loss, like the optical fiber, which gives additional attenuation. And the signal power needs to be still high enough that it can be detected by the receiver. Always keep in mind to add a safety margin here. Why? Because the fiber aging, an optical fiber can age, and the attenuation values can increase. You might have some future repairs that might be necessary you didn't know about right now. So to have a certain safety, you need this headroom, you need a margin. So knowing the transceiver, knowing the link budget, knowing which wavelength will be sent, because that defines how high the attenuation is good to make a broad assumption if a link will work. Can help for planning, but if you actually want to do a real-life deployment, always use measured values, because you cannot just assume that the fiber will have average attenuation values. So bottom line is knowing some foundations of optical networking can help IP engineers to avoid guesswork, to have a certain mental model, help with faster troubleshooting, and with collaboration of optical teams and improving handovers. And finally also handing over less tickets at our help desk. So that's it. That's the presentation. Thank you very much. Let me know if you have any questions. Thank you.
Thank you very much. I see the question here, so I will.
Hi, this is Andreas. So when you show the graph with the loss of the for the different wavelengths,
yes,
and there was a hill with the water peak. So this is based on the physical media, right?
Yes, exactly.
So are there any? You said that there are different IT modes or something, but are there any experiments with using different wavelengths and different media that would work better? Because I'm kind of understand that you are basically both to these frequencies, the wavelengths, because you already have the cables and you already have the transceivers and receivers. So we are stuck in these wavelengths. Are there any experiments in the future where the wavelengths might change and the media might change and they would work better or have a better profile or something?
Yeah, there are technologies that are in development, like hollow core fibers, for example, using different wavelengths. But as far as I know, using the current standards and the physical, the optical fibers that have these standardizations are the set standard, and there's not much playroom. There's, for example, the G.1652.D, which has at the 1400 nanometer window lower attenuation. So there are some varieties in which optical fiber you can use, and that's actually also very important in planning optical link, to know which fiber is actually laid, so you know which transceivers are the best and which wavelengths are proper to send over the medium.
Thank you. Is there any more questions? I don't see any. So going once, going twice. Thank you very much for your presentation.
Thank you very much for your time. Thank you.